Welcome. We're going to do capacitors together this week. Actually, we already did it. You just don't know it. I already shot the video. We already collected our data, but I wanted to re-record this initial part because I want to apologize. Normally when I make these videos, they're in the middle of the night, so there's no issue with noise. Today I did it midday, and it was hot as hell outside, meaning it was hot in this garage, so that there wasn't any interference with the audio. I did not turn on my air conditioner. Throughout this video, you're gonna hear a lot of external noises because the door to the garage was slightly open. Also, there's a ceiling fan up here that was on. I didn't think it'd be that loud, but it is, and it bugs me that you have to hear these distracting noises. But anyway, with that said, I'm going to continue to make them at night, so in the future there won't be this issue. And with that said, I'll say a few words about this lab. Unlike some of the others where we actually sit together and collect all of the data and record it while we make the video, all this data is going to be provided to you. So we're shaving off like 30 minutes of what this video would otherwise be, because it just doesn't serve you guys for us to spend that much time disconnecting a circuit, discharging capacitors, reconnecting the circuits, charging them up again. You wouldn't be learning anything more if we did the whole thing from beginning to end. So I went ahead and did all that on my own, got the data for you, and it will be provided to you by your instructor. What I did want to do is go through the process of how that data would be collected if you did in fact needed to do it on your own. The reason being is that technically you should have collected it on your own. Also, if you're just handed data, there may be a little confusion or not as much of a learning experience if you have no idea how it was obtained. So that is the purpose of this video. And what we are going to do is start with constructing that circuit there. And that is on page 18 of your lab manual, figure 8. And essentially all we're doing is determining the voltage across an unknown capacitor that's hooked up in series with a capacitor of known value, so that we could determine what the unknown capacitance is. And you'll be doing that with equation 19 in your lab manual. So let me put you on pause and we'll get started. Okay, so here's an overhead view of our desk with the components that we're going to be using for this first part of the lab. Actually, the same components will be used throughout. It will just be switching the combination of capacitors here. So at this point, what you should do is turn to page 18 in your lab manual and take a look at figure 8. That circuit diagram there shows what we're supposed to construct. And on the left of that diagram, you'll see the notation VB. So that is the voltage across our battery, or in this case, our power supply. And that connects to a 22 ohm resistor. Well, let's just get it set up. So out of the positive terminal of our power supply, that goes directly into one end of our variable resistor. So this is a rheostat, and you could vary the resistance with this slide here. In this particular lab, however, we're not going to utilize this as a variable resistor. We just want to use this as a standard 22 ohm resistor. So in that case, we are going to plug into these two ports here. This is not connected, has no effect. We're just going to leave that alone. And by the way, the reason why we connect or introduce a resistor into our circuit is just for safety practices. You know, Ohm's law, F is equal to IR. If we had no resistance in this circuit, as soon as we connect these capacitors to a power supply, technically there'd be like an infinite amount of current flowing through until the capacitor starts to get charged, then it would drop off. But we don't want that much current flowing through at any instant of time, so we just add this resistor and it slows it down. That's the purpose of this here. So again, referring to figure 8, the other end of this resistor, so in the figure, by the way, this is up like this. I'm trying to orient these components on the bench as closely as I can to that diagram so that there's no confusion. But this, as it is placed now, this should not be confusing. So the other end of this resistor goes into our C, and C is the known capacitor, which is placed right here. So I'm going to plug this into one end. And out of this capacitor, we want a wire to connect to our unknown capacitor. And this kind of connection is simply known as two capacitors hooked up in series. The other end of our unknown capacitor goes to our power supply, so I'm going to connect that to our negative terminal of the power supply. Of course, there's also a voltmeter and a switch connected to this circuit. I haven't addressed that yet, but if you just look at the left portion of that circuit diagram, we have just constructed it. So what we do now is connect our voltmeter and switch. So here is our digital voltmeter. Right now you can't really read the display, but we'll adjust this later. I'm going to put one wire in its ground and the other wire in its voltage port. In other words, if I was measuring current, it would be, we would have to put it in a different port and switch its function. So now it's set up to read voltage, and we want to measure the voltage excuse me, across C1. So the way your circuit diagram is, we want to go across these two wires here, of course incorporating the switch as well. Well, let's put the switch in now. I'm going to put one end into the switch. So I have two wires, and if I wanted to resemble the outlay of that circuit diagram, I would connect them here. Now, you realize that I could connect them here or a little bit closer, and that wouldn't change anything as far as measuring the potential difference, or a little closer or a little closer. So why not just put them right in here? And I just switched these connections because this red Pomona lead had a port at the other end. They could have been connected either way. So there you go. We've just constructed the circuit shown in figure 8. Now, while as we were constructing this, the capacitors were indeed being charged. And what you want to do when you start taking data is close this circuit here, and what will happen is that this voltmeter will read the potential difference across C1. Now, technically a voltmeter has infinite resistance, so when we close that switch, it should just read some voltage and be constant. But in practice, voltmeters, although they do have an extremely high resistance, in reality they're not infinite, right? So what ultimately happens is that the capacitor does indeed slowly discharge. So the lab manual instructs us to read the highest voltage that our voltmeter
displays before it starts to drop, and that is the correct voltage across C1. That is the correct voltage of interest. But what I do in these cases is I put this on max, and by putting this on max, it is going to freeze at the highest voltage this multimeter records. You can see right now it's fluctuating around 74 millivolts. By the way, not volts, but millivolts, so it's pretty close to zero, right? The highest voltage it recorded was 76 millivolts, but when I hit the switch, it's going to record the voltage across C1 and then start to drop. But it doesn't matter that it's dropping. We don't need to be quick and instantaneously catch what that highest voltage is. It's just going to be recorded on this bottom line. So let me complete the circuit and measure the voltage across C1. So, okay, should I explain this? By the way, don't worry about the colors of these wires. There's a high potential on this side of the circuit with the lower potential on this side, just by virtue of how we connected the power supply to these two capacitors. And the multimeter was hooked up in the opposite direction, so it didn't register. It was looking for the maximum negative voltage, if that makes sense. So let's try it again. I just reversed these two wires here. So you can see the highest voltage it recorded was 2.6 volts. So that would have been the voltage across C1. So what we would do after this is perform this measurement all over again. There's going to be slight fluctuations, slight experimental error, if you will, with the charging and discharging of these capacitors. So we want to get 3 recordings, average those, then use an equation to determine the actual capacitance of this unknown. And it's pretty explicit in your lab manual that when we do this trial again, we need to disconnect and discharge that capacitor. So I'm just going to plug this back in here. That's not going to affect anything. We've essentially short-circuited that capacitor, so it's discharging. And I will do the same for this one here. So they're discharging. This one has had enough time to discharge. So I'm going to reconnect it. And I'm going to reconnect this one as well. You see I have this little wire just hanging here. That's just to make the process easier for me to discharge them. This little wire isn't going to affect the charging of the capacitor. And what I'm going to do is measure the voltage across this a second time. By the way, I'm anticipating it to be significantly different, and we'll go over why in a second. So in this particular case, it's 4.08 if you use 3 significant figures. That voltage across the unknown, 4.08. So why did it jump up from, I think it was around 2 volts on the previous trial? And that was because we did not fully discharge these capacitors when we charged them up again and measured the voltage across C1. So it gave us an erroneous result. And I left that in just so that it could demonstrate the importance of discharging the capacitor before each trial. In fact, let me convince you. What I'll do is discharge, and we should get something like 4 volts if we do it again. So that's had enough time to discharge. This has had enough time. What I'll do is I'll reset this. So 6.2 millivolts, we're close to 0. I'm going to close this circuit to measure the voltage across C1. And I got 4.15 if we're keeping the 3 significant figures. So we got approximately the same voltage. And again, you can see how it fluctuated just a tiny bit, and that's the reason why we're instructed to do this 3 separate times, then average those 3 values. So the data that we just collected right now is not going to be part of your analysis. I will provide you, like I said, with measurements, but for the first part, which is indeed part 5A, measurement of a single unknown capacitance, that is this part right here. In your table, there is a spot. If I could just find my table. Okay, my table's ripped out of a lab manual. Let me go grab a table. Just 1 second, let me put you on pause. Okay, here's what your table looks like. Your V here is the voltage that we just measured across the voltmeter. So as you can see, there are 3 different rows there for your 3 separate trials that will be provided to you, and then you'll average it here, and you'll use an expression in your lab manual to get the experimental capacitance of C1. So that is what we just did right now. We just did 2 trials, but you'll have data for 3. Then you will do it again for C2, your other unknown capacitance. And we won't, well, I just demonstrated how we go about doing this, so I'm not going to do it again with simply just another capacitor, but you'll have data for C2 as well. Now, let me put you on pause and I'll get us set up for our parallel connection of 2 resistors, or 2 unknown resistors. Okay, now we are moving on to part B, measurement of equivalent capacitance of series and parallel combinations. This particular combination that we'll be doing first is the parallel connection. If you noticed, I put blue tape there. That is the only part of the circuit that we're changing for this part of the lab. So these 2 are connected, these 2 ports are connected, and what I need to do, if I follow the circuit diagram, is connect your known capacitor right here and the power supply right here. Just disregard the hookup of the digital voltmeter and switch for now. This is the left side of that circuit. So what I could do is simply move these 2 along these wires and connect here, and that is the same exact setup as your diagram. For our switch, we need that to connect here, and the other end of that goes to our digital multimeter. The digital multimeter in turn goes here. So I am just going to follow this wire and connect it there. Follow this wire and connect it here. Actually, there's really no place for me to plug in there, so I'll follow this wire. No, there's no place there either. I'll switch it like that. So we have that circuit set up, and I previously discharged the capacitors. So what I'll do is close this switch and measure the voltage across those two capacitors connected in parallel. And I got 1.84 to 3 significant figures volts. So what you would do if you were in the lab is disconnect this and short circuit each individual capacitor to fully discharge them, hook it back up again and redo it. Do that 3 times. Of course, we're not going to do that here. I'll provide you with that data. And I want to bring to your attention your table just to clarify any confusion you may have. Lab manual instructs you to use equation 19 in your lab manual to compute C1 in the first part. Then you use that same equation to compute C2. Now in this part you are going to use equation 19 again, but what C1 represents is not just C1. Well, let's see, what shall we call it? C1 represents the effective capacitance of these two connected in this way. So the effective capacitance of everything here within the blue tape. So C effective of C1 and C2 connected in parallel. So you will use equation 19 to get an experimental capacitance for the parallel connection. Then you need to compute a calculated or like theoretical capacitance and put that here. And that's going to be extremely easy. In fact, what you do is you use, maybe I'm holding your hand, doing a bit of hand holding, but you use equation 5. And look how easy that expression is. What I mainly wanted to do is bring this to your attention as well. See these two boxes? I believe that those were put there by mistake. Or they're meaningful here, but not here. I think that the author of this lab meant or should have blocked those out as he did here. You are determining C1 and C2 by measurement, an experimental capacitance, but you can't calculate it. I mean, you're using 19 to get these two values, and that's the best that we can do. There's no known or other way to calculate the capacitance, so these should just be left blank. So keep that in mind. So because again, this table does look confusing, like you're supposed to put something there. And what we'll do now is connect up our circuit in series so that we can fill out the rest of this table. So here's our next part, where we are going to measure two unknown capacitors that are connected in series. It's already, the left part of the circuit is already hooked up, and the only thing changed is within the blue tape here. So you can see a wire comes off of the known capacitor, plugs right into C1. C1 in turn goes right into C2, and then out of C2 goes right back to the power supply. Now, what we're to do is connect our voltmeter across both ends of this series connection. So one wire would go here and the other wire here. So what I could do is just follow these two. Again, there's no way to plug into this one here, so I'm just going to switch the order, which makes no difference. They've already been properly discharged. What I'll do is I'll complete the circuit, and I get a voltage of 4.57 volts. So in your lab, you would again need to disconnect these, discharge each capacitor, hook it up again, and remeasure. So you would do that for a total of 3 times. And that is it for part B. Let me put you on pause and get you set up for part C. All right, part C, measurement of the time constant of an RC circuit. So our circuit is already hooked up here, and it's pretty basic. I'll go over it. It'll just take about 60 seconds. Look at figure 11 on page 20 of your lab manual, and let's break that circuit into 2 parts, the left and the right. So focusing on the left part, what we have is our power supply, and out of the positive terminal of the power supply, we're connected to our 22 ohm resistor. On the other end of that resistor, we are connected to this switch here. By the way, we're using a different switch. The switch in the previous experiment was simply an on-off switch. This one here functions a little bit differently, and I'll show you how in a second. This wire here with this switch in a certain configuration can be connected to just this wire here, which goes to our capacitor, and the other end of this capacitor simply goes right back to our power supply, the negative terminal of the power supply. So this here is the left part of that circuit. Now the right side of the circuit is this wire here connected to this wire, and it goes right to our digital voltmeter. The other end of our digital voltmeter is connected to the other side of our capacitor. So what happens is when this switch is thrown to the left part of the circuit is complete, and our capacitor charges. Then when we throw it to the right, the left part of the circuit is no longer connected. In other words, we've just eliminated the power supply. We've hooked it up to our voltmeter, and the complete circuit then is our voltmeter and capacitor connected together. And the capacitor then begins to discharge through the voltmeter. So in this straight up and down position, neither side is connected. It's an open circuit on both ends. So what I'll do when we start is simply put the switch over to the left and charge our capacitor. Well, let me go ahead and do that now. So our capacitor is charging, and what we want to do in this part of the lab is find the half-life of our RC circuit. Now, as a heads up, and they mentioned this in the lab manual, but I just wanted to say it again, the resistance in this RC circuit is not that resistor over there. It is not our 22 ohm resistor. I won't say any more than that, just wanted to throw it out there. Read the lab manual. Now, when I throw the switch to the right, of course, I'm going to get some voltage across the capacitor. I want to make note of that voltage. It's not going to be any trouble though, because I'm going to put this on max, so that voltage that it initially reads before it starts discharging will permanently be displayed on this second line here. And when I switch the switch over to discharge, I want to hit our, I want to begin our timer, because ultimately what we want to do is determine the time it takes for half of this capacitor to be discharged, and we could determine that with voltage readings. So whatever voltage it initially reads, I want to time it from that time, from time of beginning to discharge, to the time where the voltage across that capacitor is 1/2 of what it started. And in saying that, a minute ago, I hope I didn't call that a resistor. If I did, I'm correcting myself now. So let's see. Normally, if we're in the classroom, what I have students do is like, you're usually in a group of 3. Each person will have a different function or role. One person will hit the switch and start the timer at the same time. The other person would take note of the max voltage divided by 2. Maybe another student would observe the voltage drop, and when it hits that target value, the 1/2 of the initial, they would shout out to the individual with the timer, and they would stop the clock. But I'm going to do all that simultaneously, and we'll see how it goes. So let's see. All right, we're fully charged, and I'm going to begin discharging. 1, 2, 3. So max voltage is 6.130. 6.130 divided by 2, that is 3.065. So I want to wait for that to get to 3.065. We'll call it 3.07. 3.07. 3.07. We're almost there. Okay, I stopped it at 3.08, which was pretty damn close. In fact, if you saw, it was changing by 100ths of a volt within a tiny fraction of a second. So the error involved in this is just your reaction time. And my timer is reading 31.66 seconds. And obviously in this case, that last 6 in the 100th place of our timer is meaningless, right? My reaction time isn't that quick. But anyway, 31.6, or we'll call it 31.7, that would be the half-life of this RC circuit. So in the lab, you would disconnect, discharge capacitor, reconnect, then charge capacitor, flip the switch, time it. You would do that like 3 times. But again, that data will be provided to you. So let's get on with the next part. Hold on, we'll put you on pause. Okay, so for part C, there's actually 2 parts. We just did part 1, now we're gonna do part 2. If you look on your lab manual on page 17, you'll see figure 7. Well, although figure 7 shows Q versus T, what the manual instructs us to do is do plot V versus T, and it will have the same general shape as that curve in the figure. And the way we do it is simply, well, not so simply, but it's done in the exact same fashion as the part 1 of C, the part we just did. The only difference is, instead of finding the time it takes for the capacitor to discharge to half of its voltage, we want the time it takes the capacitor to discharge at various times. Not at any specific time per se, just various times, so we can plot them and make that curve. So your table asks for 5 data points. I'm going to supply you with more, just because 5 seems rather low. But I'll show you how I went ahead and collected that data. What I'll do is charge the capacitor, and I realize that the complete circuit is out of frame, but I want you to just focus on the digital multimeter for now. So I'm charging the capacitor, and again, what I'm going to do is flip the switch over to the right to disconnect it from the power source, and just hook it across the digital multimeter and time it. Now, let's say I was shooting for 10 data points. I would predetermine what time values I want, say 0, 5, 10, 15, 20, 25, 30, 35, 40, and 50. I would need to keep an eye on my stopwatch, and at those specific times, take note of the voltage across the capacitor. Now, it can get tricky if the capacitor is discharging rather quickly, but I've managed to do it at 5-second intervals. So let me put it on its max function so I don't have to worry too much about the initial T equals 0 voltage. It'll permanently be displayed there, but I'm going to hit the switch. So at 5 seconds, it is reading 5.0. At 10 seconds, it is reading 4.4. At 15 seconds, it is reading 3.9. At 20 seconds, it is reading 3.5. And so on and so forth. I would let the clock run to 50 seconds or however long I wanted it to go, and record those voltages at that specific time. So there, I believe, is quite a bit more analysis in this part of the lab, but nevertheless, that is how you collect the data for it, which again will be supplied to you. So let me put you on pause for a moment.
Okay, that's it. We've concluded this portion of the lab. I hope you found it useful. And I apologize for that background noise. We're going to eliminate that in the future. But until next time, I'll see you.